Greetings and welcome back. Today we'll be looking at anti-Markovnikov addition. In order to understand anti-Markovnikov addition, first we need to recall what Markovnikov addition is. I'm going to shorthand this as Markov. Markovnikov addition is if you started with an alkene and added, say, H plus and Cl minus. What we found in the past is that the H would go on the side with more H's in order to make the more stable intermediate carbocation, and then at the very end of the day you ended up with the H on the side with more H's, which in this case would be the right side, and the other thing, which in this case is chlorine, goes on the side with less hydrogens. So we would add on this guy right here and this guy right here. So many decades later, we've also discovered a way to add H and halogen in an anti-Markovnikov fashion. That is to say, putting the H on the side with less H's. So in this case, what we're talking about is starting off with an alkene and adding the alkyl halide so that we have an H that goes on the side with more carbons and a halogen. In this case, the only way we have to do it so far is with a Br that goes on the side with more H's. So this is opposite from the way that we put them on initially. And the way that we do this is actually through a free radical mechanism. And it's a free radical mechanism that we have never spoken about before, and therefore I'm not even going to give you the mechanism for this. If you'd like to know about it, you can come ask me about it during office hours and I'll explain it to you. But for the sake of this, let me just let you know that we can only do it with HBr. It doesn't work with HCl. And we add it with a peroxide. Peroxides, just like hydrogen peroxide, involve two oxygens in a row, and because both of those oxygens pull really hard on those electrons, they end up splitting that bond in half, making unpaired electrons or free radicals. So this is a free radical mechanism. And one that we will speak about at the very end of Organic 2. But the way that this works is it gives us anti-Markovnikov addition so that we can put the bromine on the side with more H's and the H on the side with less H's. So it does exactly the opposite of what Markovnikov addition does. The way that you might see peroxides written is either ROOR, or it could be some carbon, oxygen, oxygen, carbon, or sometimes it's just written as peroxides. All right, and that's it. That's how we can add on an HX in kind of the opposite way from how it wants to normally add. Again, this was called Markovnikov addition because the chemist Dr. Markovnikov was the first one to notice that this is how things normally happen. And I believe that from a time point of view, it took us about 50 or 60 years to figure out a way to add it the other way around. So the only other addition that we've done at this point is adding H and OH. So let's look at that when it comes to Markovnikov and anti-Markovnikov. So once again, let's go backwards to Markov really quickly. And we had two ways of adding H and OH in terms of Markovnikov addition. And the best one was to add the mercury diacetate and water followed by sodium borohydride. This was oxymercuration demercuration. So in the first step, we put an OH on the side with the carbons, so that would be over here, and we would put a mercury on the right side, or the side with more H's. In the second step, we kick that mercury off with H, and we would end up attaching this OH on the side with less H's, and the H on the side with more H's. So let's look at how to do this in anti-Markovnikov fashion. So starting with the same alkene that has more carbons on the left and more hydrogens on the right, let's go back in time a second and talk about how alkenes react. So remember, alkene addition always starts with the alkene that has a pi bond. A pi bond is loosely held electrons that are kind of floating around in space a little bit. So I'll kind of draw that pi in a little bit for us here. And what's attracted to pi bonds? What's attracted to electrons? It's electrophiles. So a molecule that has an electrophile is BH3. In this case, the boron doesn't have a full octet, therefore it's an electrophile. and this pi bond, or these electrons, are attracted to the electrophile, and therefore we would make a new bond. Just like we've done in the past with H plus or with mercury or whatever, the place that the first thing goes when we're adding on to an alkene is to the side with more H's. And so we tend to make a bond to the right side first so that this can become the more stable carbocation. So in this case, and if you're taking notes, don't write this down quite yet, it would seem logical that we would form this guy right here, because the C plus on the left would be most stable. But that would make the boron negatively charged. And so having a negatively charged boron that has too many electrons, this close in proximity to a C plus that doesn't have enough electrons, is an easy fix. This boron would just kick one of those hydrogens off, but instead of becoming an H minus, it would go straight over to that carbon and bond the boron over there. So what we would get would be that we'd have the H come onto the side with less H's, and our boron would go on the side with more H's. And so, in essence, both of these mechanisms that I've shown here happen at the same time. The electrons from the pi bond are shared with the boron, giving the boron too many electrons and a negative charge, and therefore it would immediately kick these H's off to that carbon. So instead of considering both of these mechanisms separately, which they definitely do not do, what happens instead is that this happens simultaneously. And realistically, we have our boron right here, and the electrons from the pi bond are attracted to the boron, which at the same time kicks that hydrogen off over to the side that isn't making the new bond with boron. So you can also think about this in terms of kind of the big part of the BH3 goes with the little part of the alkene. The big part of the alkene goes with the little part of the BH3. Just another way of thinking about it. And so what we would get from that would be that we would have a BH2 attached on the right and an H attached on the left. Ooh, excuse me. And so at this point we haven't added on an OH or anything like that, but we have a second step to this reaction. And the second step to this reaction, the first step is the BH3. Second step, we would add in OH minus, usually NaOH, and hydrogen peroxide. And what these guys do in a very complicated mechanism that I'm not going to worry about is that they displace the BH2 and replace it with an OH. And they don't do it with a backside attack, so they end up with that OH attached in exactly the same place. So once again, what we have added is H and OH. And the way that these guys have gone on in terms of regiochemistry, that is to say where they show up, which side of the alkene, is that the OH goes on the side with more H's and the H goes on the side with less H's. All right, so there's a couple more things to consider in here. The first is that borane, which is BH3, is really, really reactive and quite toxic. So what we'll often do is put it in with THF, just because THF kind of follows it along and makes it less reactive, less toxic. It'll still do the reaction, but this right here is furan, and this molecule right here with 4 more H's is tetrahydrofuran. So that right there is what THF looks like. You don't need to know that structure, but just so you're not surprised, BH3 is what reacts, but BH3 attached to THF is the way of having borane that's less dangerous to use. All right, the other thing to notice is that when we added these on, we add the H and the OH together because the H and the BH2 come in together from the same face. So think of this molecule as sitting down either on top or below together, therefore the H and the BH2 come in from the same face, and so the H and the OH come in from the same face. So this is something we can see a little bit more easily if we do this reaction starting with an alkene that is in a ring. So let's do this. We'll put an H and a CH3 here. When we add in our BH3.THF, so our borane comfied up to THF, what we'll do is we'll put the BH2 on the left side. So here's my H. The pi bond would be attracted to the boron. The hydrogen would go over here. Again, the reason that it goes on in this way is because the boron goes on the side with more hydrogens, the hydrogen goes on the side with less hydrogens. And that's how this is going to go on every single time. So sometimes it goes on the right, sometimes the left, sometimes the top, sometimes the bottom, but the BH2 part of it will always go on the side over here that has more hydrogens. So this would attach in a way that gives us, but note, this guy has to either come in from the top or from the bottom. Because this is in a ring, we can see how things come in for sure. So let's say it comes in from where you're sitting right now, which is from your point of view, the front. Well, it would push that pre-existing H backwards. It would push that pre-existing methyl group backwards. And we would have our new BH2 attached in the front over here. We would have our new H attached in the front on this side. When we use that second step, in which we add in some peroxide and some hydroxide, what happens is that we replace that BH2 with an OH, and it stays in the exact same place. So what we can see in this case is that the two new things that we've added in, which are the new H on the side with less H's, right here, and the new OH, which came on the side with more H's, those guys came in from the same face, they came in together, and so the stereochemistry of this molecule ends up being such that those two guys come in together. We say that this is Syn addition, but from the point of view of a ring, think of it as the fact that these two things are cis to each other. The two new things we add are cis to each other. All right, let's practice that, and if you have any questions, please bring them to the class. Thank you very much, and I will see you soon.